Hello to everybody, microphone is active, so let's go to Gauss-Green theorem. So this is the slide I prepared, and so I recall you the content of Gauss-Green's theorem. Basically, if you just look, I have a problem with my pen, but if you just look at the formula is this one here, the purple one, that says that the circulation of a field F on a positively oriented circuit C is equal to the double integral on the internal part of the curve D of this difference of dxF2 minus dyF1. Okay, I already explained that this is the z component of the curve of a three-dimensional vector field, and this will be the starting point to generalize to Stokes' theorem. And so, as an example, positively oriented for a simple closed curve, it means in general just anti-clockwise, even though you have to be careful about that, because if you have holes, the contours of the holes can be positively oriented when they are clockwise oriented. So in general, the true rule is the following: look at where you are, think of you as being on a bicycle, and then put your left hand just very shy, your left hand in your left direction, and then your left hand should fall inside the curve, in the internal part of the curve. Okay, this is basically the equality of these two integrals is very significant, because these two integrals apparently have nothing to do with one another. So at the lowest level, you can you can think of the Green's theorem as just a tool to turn a difficult integral into an easier one. Which is the more difficult, which is the easier one? It depends on cases. And then we had an example in which the integral, the direct computation of the circulation is quite cumbersome integral, but it can be done. On the other hand, using Green's theorem, the computation was extremely easy. So, and there are examples of this type and also other examples. Okay, what I want to do now is give you a sort of proof, not real rigorous mathematical proof, but a simplified proof that is generally quite liked by physicists. So let me write here what I mean. I mean that I want to give you formal proof. Okay, formal proof of Green's theorem. Here, formal means exactly not mathematically rigorous, but I think you can see really the meaning of the Green's theorem more from this formal proof than from the rigorous one. I think you don't have to know proofs of the theorem, at least not of all the theorems. You are going to be engineers, so not mathematicians. So why did I choose to give you this formal proof? Because, in my opinion, it clarifies the mystery of this identity between two integrals that are so different. Okay? So, the idea is the following. Consider the problem of computing the circulation of a field. So, consider the problem of computing the circulation of a field F. As usual, F is F1, F2. Let me put immediately 1, F2. And I stress again that when using the Green's theorem, the field must be planar. So we are in 2 dimensions. Okay? Oh, I left here the very funny effect. F1, F2. Okay, the circulation of a planar field, okay, on the regular, remember, means that it possess a tangent vector in or at every point. This is regular for us. So, circulation of a planar field on the regular circuit, let me call it C. Okay, so picture, you have this C, this is the circuit, and you want to compute the circulation. And the first observation is the following. Consider a grid. Okay, now I will display a grid here. So this is a grid. Okay, of course, ideally it should be very thin, but this time this is not really the case. Okay. Okay, so I want it to be a little more thin, but okay. So we plug our circuit into a grid. Okay, and now, instead of considering just the circulation on the grid, we consider circuit in this way. Let me use it the brown. So consider, for instance, here the circulation on this circuit, which is made of a part which is on the grid and another part which is on the original contour C. So let me call it Ci, for instance. Okay, this is another circulation of the field. But then you can imagine also a further circulation on an adjacent circuit, which is again partly on the grid and partly on the original circuit. So you start from the part on the grid that gives you the orientation of this new, and you find this guy here. So notice that the side, so let us call it Cj, the only side which is common to the circuits Ci and Cj is a side not on the original circuit but on the grid, and it is run through two times in opposite direction. In the green circuit Cj, it goes rightwards, while in the green circuit, in the brown circuit Ci, it goes leftwards. So the two contributions, so the key reasoning here is that the two contribution given by the only side which is in common to the two circuits Ci and Cj cancel each other. So this is the key observation of all the proof. Once you understand this fact, then you understand everything. So vice versa, if you did not understand this, stop here and try to reason or repeat with the video and so on. We can also add another example. Here we go to consider another circuit. We want it to be positively oriented, which here means counterclockwise. So the correct orientation here is here, here. And again, the common side is run through in the opposite direction. So these two contributions cancel each other. And then you go for now the last, and then I stop. The last circuit you can consider is this one. So you start from the original curve, and again you see in the common side the two directions are opposite, so the two contributions cancel each other. So so the key observation coming from this picture and this reasoning are the following. So consider the sum of all circuitations of the field F on all circuits generated by the grid in the region internal to the original circuit C. Okay? So the sides belonging to the grid and not to C are run through exactly twice in two opposite directions, so that their overall contribution is zero. This is the point. Okay, there was a problem here with the correction, circuitation. Oh, sorry, circulation. In English, sorry. Circutazione in Italian. Circuitazione and circulation. Okay. Oh, circulations. Okay. So, at the end, so eventually, the only survival contributions are those of the side on the original curve C, on the sides of C. Namely, so as a final formula, we have the following, that the circulation we had to compute originally, F times dr, can be written as the sum on all i's of circulation on Ci F times dr. This is an exact formula. You put whatever grid, and by this effect of pairwise cancellation of contribution, you have that the only surviving contribution are those on the grid. They are the only ones that are run through only once and not twice. For the sides on the grid, you always have that they are run through twice into opposite direction. So the only surviving side are so-called, so to say, the curved one. Okay? So now, let us compute a generic Let us now compute a generic contribution of an internal circuit. Okay, so we have a rectangle. Think, for instance, of this guy here. This guy here, which is take a rectangle which is totally inside the curve. So here we only have contribution that cancel. We want to compute this CI. And so let me provide a picture of CI, for instance. This is CI. And this is positively oriented like that. And now right here the coordinates of the angles, and here you start from x, y, and here you have x plus delta x, y, this is the step of the grid. Here you have x plus delta x, y plus delta y, and here x, y plus delta y. And of course you have on all this circuit the field to be computed, which is F1, F2. Okay, and this is CI. So you want to parameterize this circuit, and this is made of 4 sides, and of course you can parameterize the 4 sides in different ways. So here you can find T, Y, with T in x, x plus delta x. Okay, this is R on the side. On the side here. And so on and so on. So here you have here R dot is equal to 1, 0. This is the velocity here. Here the velocity is 0, 1, proceeding in analogous way. Here it will be minus 1, 0, because you're going backwards along the x-axis, and here R dot equal to 0 minus 1. Very simple. And now let us go for computing the circulation. So we have that if you compute the circulation on CI of F times dr, this is equal to the 4 sides. So first you have F1, F2 times 1, 0. Here you are here on this side. And in dt, t is going from x to x plus delta x, plus you go to the second side, and then you go from y, y plus delta y, and here you have f1, f2, and times 0, 1, dt plus, this time you go from x plus delta x up to x or and here you have f1, f2 times -1, 0 plus, so, and the last you go from was 1 plus delta y, y, f1, f2 times 0 minus 1, and so on and so on. So what you get at the end is, in the first integral, you got the integral from x and x plus delta x of f of so this is ty dt plus y plus delta y, and this is, sorry, f1, and this is f2 x plus delta x t dt, and then you have minus x plus delta x f1 f1 of t y plus delta y dt, and then minus y plus delta y f2 x t dt. Okay, so let us go. Let us do it. We consider just the first and the third, and here what you have is the integral between x and x plus delta x f1 t y minus f1 t y plus delta y. Okay, this is wrong, and I have